Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh, and very good day to all students. I am Dr. Jeffrey from the Faculty of Manufacturing Engineering, FKP. So let us continue the offline lecture for this chapter 11, the characteristic, processing and application of composite. This is the part 3, the last pre-recorded teaching video from this chapter. So in this video, we will expose further with composite processing focusing to the polymer matrix composite, some of the application and sample of structured question from this chapter. So before we proceed further, here are some of the basic guide about the processing of composite material. As a rule of thumb, before we combine the material for producing the composite, typically produced separately before being combined into composite. So meaning to say, we make the fiber first, or we make the particle first, and we make the matrix at the other side. Only then we can combine both of these phases into composite material. So next, for CMC and MMC, due to the nature of matrix material, normally to produce MMC and CMC, we will employ the powder metallurgy technique, where we combine the dispersed phase with metal or ceramic, which prepared beforehand in the form of powder. Then we compress them and proceed to sintering for solidification. More simple and commercially applied in industry are the polymer matrix composite PMC making, which employing molding process that combine the polymer matrix and dispersed phase with the help of molding method. Here also some of the specialized process that have been developed for fiber reinforced polymer composite. The following slide on processing will be focusing only to the manufacturing of FRP, the fiber reinforced polymer PMC, considering their simplicity and commercial availability in the market. So for PMC, the polymer matrix composite manufacturing, focusing to the fiber reinforced polymer, they are basically main processing method that can be generally classified into either open mold method and closed mold method. There is two options of processing for PMC. Okay, as you can see here, for open mold method, for LRP PMC manufacturing, okay, the open mold method here, we will have the hand layup method. This is the most simple method. The pultrusion method, the filament winding method, the second process, and then the spray method. This is all for the open method, open approach. And for the closed method manufacturing for PMC, okay, we will have various options of processing, like the Prepreg Forming. Okay, I will introduce you with the term of Prepreg, the Pultrusion, the vacuum molding, pressure molding, sheet molding compound, the SMC, and resin transfer molding, the RTM here. All right. So for this slide, general view about the open mold process, basically only one mold part, either the male mold part or the female mold part, is required for executing the open mold process. Okay, maybe we can call it as what kind of pattern we need for our product. Okay, so for your general information, normally for the female part, mold part, it have the enclosed part here, something like this. All right. But for the male mold part, it have the extra portion here, something like this. This is the male mold, and then this is the female mold. Okay, so for the open mold process, we require only half part of this mold, okay, for us to make them as the pattern for our product. So the product shape will be in accordance to the shape of the mold. The half mold part can be made either from the wood, reinforced plastic, okay, for longer run or utilization. We can also use the sheet metal or electrofoam nickel. All right. So using the mold will ensure the final part of the resulted product surface will be very smooth. Usually will be very smooth. Yeah. So the role of using mold here, even for open mold process, to give shape and for better high surface quality. All right. So first, the mold release agent need to be applied on the surface of our mold. Okay, it can be silicone based, polyvinyl alcohol based, or many others. All right. Second, okay, the shape, the step of using the open mold process, we apply the unreinforced surface layer, or we call it as gel coat for better surface quality. All right. First, apply the mold release. Okay, and then second, we apply for the unreinforced surface layer. We call them as a gel coat. All right. So we go proceed to the first open mold method. Okay, here the simple method for fiber reinforced polymer manufacturing, namely the hand layup process. As you can see here in the figure, all right, the basic setting for hand layup process, we need to have die. Okay, this is our die. All right, in accordance to the final shape that we want, and the roller, okay, to distribute, okay, the matrix to the fiber face. Normally we pour the matrix in the form of liquid, say for example the thermoset matrix, the epoxy, the polyester, so on and so forth, to the reinforcement part, and then we roll the matrix together with the reinforcement for better distribution of the matrix wetting. The resin and fiber are placed manually against the die surface, and then air is expelled with squeegees or roller. We call the roller as a squeegees or roller, and if necessary, multiple layer of fiber can be placed. The fiber tape, mats, or fabric are then saturated with a polymer resin, whereby we already combine between two faces. All right. Then we roll it to assure for good contact and freedom from porosity. By doing the rolling here, using the roller or squeegees, we eliminate all the voids and also porosity. Later, after we perform this combination between the matrix to the reinforcement, we cure to harden our composite at room temperature, or can also be accelerated further by heating it at the autoclave. For this method, the void content or the void volume are typically about 1%. It's quite high. So employing this method, we also can introduce to form core for complex hollow shape. So if you want to have the hollow shape, so make sure that our pattern must be supplied in the shape of foam core. Thus, basically, this method can produce all shape of product that we wanted. So this process, the drawback is quite slow as it manually performed, and the quality of the end product is basically depend to the operator skill or the labor skill. Some of the product that we apply for the hand layup in manufacturing process are like the boat manufacturing, the A-frame component, the truck bodies, tanks, fiberglass swimming pools, and many others. All right. So for the next slide, in this slide, we actually explain at the prior, it's already explained at the prior slide just now. Just to summarize, the hand layup process is very low technical or technology method that already been applied for the past 15 years ago. To perform this method, we need to have first and foremost the open mold, and then apply first the mold surface with the gel coat for easy product release after the curing process. And then we lay down the fiberglass reinforcement here on top of the wooden. On top of the wooden, we lay down the reinforcement layer here. All right. And then next, we pour the polyester resin or our thermoset resin as one of the thermoset plastic resin, and let start to roll it. We roll it until we got a very good compaction, and then there is interaction between the resin and reinforcement. Later, we let it dry and cure. So you can even produce bigger car or truck bodies by just using this manual method. So certainly this method has a drawback as it is manually done and very labor intensive, and it requires a very good skill of labor for better product quality. All right. So the next method to produce the composite by using the open mold process is filament winding process. So in this process, the continuous fiber reinforcing fibers, the continuous reinforcing fibers are accurately positioned in a predetermined pattern to form the hollow shape, usually in the cylindrical form or cylindrical shape. We can call this unit as a mandrel. Okay, this unit as a mandrel. And then we apply and then supply the fibers in the continuous manner. All right. The fibers was supplied either as individual strand or as a thongs. And then before we applying to the mandrel, it is first fed through to the resin bars. Okay. We fed through, we wet the fiber with the resin, okay, at the resin bars, okay, then continuously wound the fiber onto the mandrel, okay. We wound the fiber onto the mandrel, usually by using automated winding equipment. After the appropriate number of layers have been applied, the curing step is carried out, similar like the hand layup process, in an oven or at room temperature, after which we remove the mandrel after finish the drying process or curing process. So as you can see here, there are various kind of winding pattern. We got the helical winding here, circumferential winding, or polar winding. This all about how we create pattern to the create pattern of the fiber on the mandrel. Okay, and then for sure, okay, certainly by having different kind of winding pattern, it will give different characteristic of mechanical properties. So normally, the composite product produced by using this method possess very high strength to weight ratio. We can produce the pressure vessel, the rocket motor casing, storage tank, whatever in the form of cylindrical and pipes by using this method. So these methods are automated with higher productivity, high degree of control uniformity, but due to the automation, we can expect that this method quite expensive for composite production. So this is the depiction of the filament winding process. As you can see here from the figure, we need to have the rotating mandrel here. Okay, this is we call as our pattern or rotating mandrel. It is rotated during their operation. The nip roller for fiber adjustment. Okay, this is for the nip roller where we can compact the fiber to give what we call that good alignment. Okay, when we do the winding. The resin bars. Okay, here to contain our resin and the moving carriage and the fiber supply. The fiber supply and then the moving carriage, they move together during the process. Due to the automation nature of this method, we can employ the CNC winding setting. CNC, the computer numerical control, sometimes up to 7 degrees of freedom. So meaning to say, the direction of the winding can go up to 7 directions, especially for intricate and complex engineering product making. All right. Some of the process variable related with this process are the angle of the fiber wrap, ratio of carriage speed to rotational speed, and many more. So the last method for the open mold is spray layup process. As the name implies, okay, here, they are combination from the spraying method, okay, we spray with the hand layup method. Let us further explore this method. In spray layup method, the fiber is chopped. Okay, we have the chopper here in a handheld gun and feed into a spray of catalyzed resin. Okay, the fiber chop here, okay, at the very high speed, and then we supply the resin, the polymer resin, from the accelerated supply here from the hose here, directed to the mold. Say, for example, this is our mold. Then the deposited resin with chopped fiberglass, we left it into cure at room temperature. A spray gun has supplying the resin into converging stream, into which the fiber roving is chopped. Okay, so please bear in mind we got two supply inlet here. First to supply the resin, and then the second supply is to supply the chopped fiber. This method can be robot automated for highly reproducible manufacturing. Labor cost is lower than the filament winding process, and this method are cheap and fast, but producing lower fiber volume fraction with high void content. Okay, all right. So we already finished discussing the possible method available for open mold method for FRP PMC manufacturing, fiber reinforced polymer, polymer matrix composite manufacturing. Now we move forward to the closed mold method. All right. So for closed mold method, we will have the prepreg production, pultrusion method, vacuum bagging, vacuum infusion, compression molding or match die molding, and resin transfer molding, RTM. Let us first start with the prepreg production. Okay, so at first, we need to understand the terminology of the prepreg here. What is the prepreg? Okay, so prepreg is the industrial term for continuous fiber reinforcement that pre-impregnated. In the layman term, we pre-wetted them with the polymer resin that is only half cured. So when it comes to the product making, only then we cure them fully. Okay, why half cure? It is because we can mold them according to the product shape and continue to cure it until full cure. All right. So normally prepreg is supplied in the tape form. All right. So that the manufacturer can mold it and fully cure into final product without having to add any resin. So this is a good option for clean manufacturing in comparison to open mold method like the hand layup and spray method. Okay, because in those method, It is really labor intensive and also quite dirty process. Okay, so prepreg most commonly used for the structural application, like for aerospace and automotive. So this figure showing you how the prepreg look like. They supply in the tape form. So it's very exclusive look of the carbon fiber that impregnated with the resin, but in the half cured supply. So the following slide will explain you on how to produce the prepreg. Okay, there are three important principal steps. Manufacturing begin with the collimating a series of spool wound continuous fiber tow. All right, fiber tow are then sandwiched. Okay, this is the supply of the spool fiber tow, and then go to the next step. All right, they are sandwiched and pressed between the sheet of release and carrier paper using the heated roller. So this process is similar like polymer calendering process, as you can remember. Okay, during the previous chapter 10. Okay, then the release paper sheet has been coated with a thin film of heated resin solution to provide the thorough impregnation of the fiber. So the prepreg product is basically the thin tapes consisting of continuous and aligned fiber embedded in a partially cured resin. So typically, the prepreg has a thickness at the range between of 0.08 into 0.25 millimeter. It's not so thick, very thin. With tap width range at between 25 to 1,525 millimeter, and then the matrix resin content are just lies at between 35 and 45 volume percent. Not many, yeah. All right. So the second process for the closed mold fiber reinforced process is the pultrusion process. All right. This kind of process is basically suitable to produce the rod and beam having a simple shape product with a continuous cross section, such as round pipe, rectangular, plate, or sheet shape. The process is automated with very fast rate, about 1 meter per minute of production rate capacity. So pultrusion process is very fast process. Okay, so some of the application using this kind of manufacturing process are like in the making of sporting goods, all right, such as the golf club shaft, vehicle drive shaft, the ladder rail, and structural member for vehicle and aerospace application. All right. So in pultrusion process, basically the continuous fiber are pulled through. Okay, some similar like the prepreg operation. We have the supply of fiber in the roving. Okay, so they will pull through the resin tank. The resin tank is located here where we supply the polymer matrix. We wet the fiber before entering to the preforming. Preforming is located here. What is the function of the preforming? Preforming is to give a shape definition and to compact the fiber. This is the preforming die. And then we proceed to the oven for curing. So curing of resin is basically accomplished almost immediately. So the pultrusion process can be automated for continuous product manufacturing. Okay. So next, this slide will guide you on how to describe the pultrusion process step by step. As you can see here, there are 5 important sections in this typical pultrusion manufacturing line. It will start with the fiber roving supply. This is the first section, followed by the resin impregnation tank. This is the second section, preforming die, the third section, the curing die, the fourth section, and the pullers as our finisher as the fifth section. To describe the pultrusion process, it starts with the rack or creel of the fiber roving glass. Racks or creel of holding rolls of fiber roving glass. The continuous fiber is then pulled through the resin tank. Okay, take this as a keyword. Pull through the resin into to pull through the fibers into the resin tank, where the fibers now is impregnated with the resin, where the fibers is now wetted by the resin. Next, the wetted resin will undergo the preforming die to adjust firmly into our required shape. Then proceed further through a heated die where consolidation and curing will take place. After curing, the pultruded composite profile was pulled by the gripper, okay, here the gripper system, before being cut off by the automated saw. All right. So the next closed mold process for FRP PMC is the vacuum bagging process. Okay, as you can see here, as the name implies, we need to perform this at the closed container so that we can do some sort of vacuumized action. All right. So the vacuum bagging method, also known as the pressure bag molding, also known as pressure bag molding. The principle of this method is we start with the tape and fabric is being placed in a die and later formed by bag molding. We place the fiber, we place the tape and fabrics on the die and later we form it by bag molding. Okay, this is your fiber. Okay, this is the die. Okay, the die. The high pressure of gases or vacuum are introduced to force the fiber splice together. So we will have the vacuumized, we vacuumize or we force the fiber with the supply of air so that it establish the good bonding between the matrix and also the fibers. And we proceed to curing. Okay, this method is applied for manufacturing of a craft, skin, and boat hull. Okay, the following figures show the principle of the vacuum bagging, as simple as this. All right, so vacuum bagging is basically the extent of wet layup process, but with better consolidation due to high air pressure or vacuum effect. For matrix in vacuum bagging, normally we use the phenolic resin or epoxy resin, okay? Phenolic resin or epoxy resin from the thermoset family. However, the drawbacks of having this method is a little bit pricey due to we require many kind of consumable to perform the vacuum bagging operation. We need to have the additional sealant tape here, all right? The breather fabric, perforated film, and many others to perform this vacuum bagging operation. Okay, so next, this is the other extension of vacuum bagging process, okay, whereby in this method we supply the resin to the vacuum bag system through the infusion channel. Okay, this is our infusion channel. Okay, this is vacuum infusion process. And then the vacuum bagging operation will help to distribute the resin that we supply just now to all the reinforcement fiber through the vacuum effects. So as you can see here, very large part, like the boat hull here, okay, the one whole ship can be manufactured by using the vacuum bagging operation. Okay, the whole ship hull can be produced using this approach. So the next process, the other closed mold process is the compression molding or match die molding. As you can recap in the open mold method, we just require only one part of the mold, either as female mold or male mold. Okay. In closed mold, the male and female mold are present together for match die molding. You see here, there is the male part, okay, and then this is the female part mold. All right, they present together to perform for the close match die molding, but only single part of mold, either male or mold in, okay, this is for the open mold. For this method, the short fiber or mat we place into at two parts of the die, then we close the die. All right, the composite shape is formed. This process can be performed very fast and able to produce even complex or intricate shape depending on the match die mold design. So by using this kind of setup, we require very inexpensive tooling due to low stress in processing. Okay, this is the putty like the polymer soft material in comparison to metal processing. Okay. So the last type of closed mold processing method for fiber reinforced polymers manufacturing is the resin transfer molding. Okay, or in short, we can call them as RTM. RTM is not the TV station, but the resin transfer molding. In resin transfer molding, the dry fiber preform. Okay, first we put the dry fiber preform here. Okay, we place in the closed mold where the upper male mold, this is the upper male mold, will clamp the first female mold. Resin then is injected here, all right, into the cavity. We call this empty space as a cavity, all right, to wet out the fiber fabric. Then the fiber inlet is closed to allow the laminate start to cure. All right. So as you can remember here, all the process related with polymer matrix composite manufacturing will require the curing process. Only then we can harden the structure of the composite into the solid structure. All right. So for this method, both the injection resin and curing stage can take place either at the ambient room temperature or at an elevated temperature. Okay, so this process can be performed at room temperature or at higher temperature. So now we finished discussing and understand the whole related open and closed mold processing involved in FRP composite manufacturing. Before we proceed to the next slide presentation on the application composite, maybe let us take a break for 2 minutes to watch a YouTube video presentation on 7 reasons why we choose the composite material in our engineering application. This video is just for the educational purpose. All right. So let's have a look. Okay. After watching a YouTube video just now from the NASA, we can understand now why composite are the material of choice for many high demanding engineering application. So in specific class, by focusing to fiber reinforced polymer composite, there are several demanding application as following. All right. For aerospace application here, all right, much of the structural part of today airplane and helicopter are basically consist of advanced fiber reinforced polymers. All right. For automotive applications, say for example, for the car panel, bumpers, and truck caps are made from the FRP. Okay. So for sport and recreation, the fishing rod, the high performance fishing rod, the golf club, shaft, helmet, skis, bows, and arrow are now made from FRP. So what else? So today, the recent, what we call that, hobby among all Malaysian to bike the cycle. So cycling, very high performance bicycle. They are all made from fiber reinforced composite. So look at here for an aeroplane manufacturing, almost 50% parts are basically made from the composite material. This is all because the awesome properties that composite can offer for the aerospace application. So next, for automotive application, composite material were used in automotive thermoplastic-based body panel, composite rubber tires. Okay, the tires here that we use for the rolling safety are basically made from the composite as well. The composite based on rubber material. The composite glass windshield here, all right, and steel based safety shell and many other parts, all made from composite material. For following slide, I will just share the picture for all the application using the composite material. All right. As you can see here, sink in your house, kitchen are made from composite. Sinks in the chemical laboratory are made from the fiberglass based composite. First to reduce the cost and then to reduce the weight, and at the same time by using the fiberglass due to their inertness, we can avoid them from the chemical reaction. Okay. So the wind turbine here are made from the composite because of the lightweight characteristic. The marine boat and ferry are all made from the composite nowadays. All right. So the carbon fibers reinforced epoxy PMC for ultra lightweight leg prosthesis here. Okay. Help the athletes compete at the highest level. As you can see here, for the athlete having no leg, they use prosthesis for better performance during sport. These prostheses are being manufactured by using the composite material. All right. This slide showing you the evolution of tennis racket from the metal base long time ago into the application of wood as a racket to now all made by using the composite material. All right, for better sport performance. Why we look forward to use the composite? Because composite are very lighter and then it gives a very high performance to the sportman or sportwoman, and then at the same time it offer for the very high strength. Okay, so next we have the composite fishing rod here. All right. For better strength with superior resilience. As you can remember back the terminology of resilient, the deformation happen only at the elastic region. So composite can offer this kind of behavior. So the space shuttle, many high temperature part, like the space shuttle engine inside here, the nose cone here, are made from the CMC, the ceramic matrix composite. for better durability at higher temperature environment. The skiing body by using the fiberglass reinforced composite in the form of sheet molded compound. Okay, we can use the composite SMC to produce the ski body here. All right. Next, for the fighter jet, the wing part, the braking parts and others are all made from the composite. In the Corvette left spring, okay, in our automotive car also are made nowadays from the composite material. At the same time, it will significantly resolve the problem related with corrosion and degradation. And then because of the lighter weight of the composite, it will produce the high performance of the car with very good fuel saving. All right. So the durable and lighter snow skis are made from the composite material for I-beam for the structural building nowadays made from the composite material. Okay, and last but not least, the pressure vessel. Okay, as you can see here, what are the best process to produce this pressure vessel? Okay, by using the open mold, as you can remember, the filament winding method process. Okay, so we basically almost at the end of the part 3 lecture. So let us view some of the revision and question related to this chapter. All right, so we already covered the processing, the characteristic, the application of the composite. So some of the question here just for the self-wonder exercise. Okay, please discuss the advantage and the drawbacks of using composite in the following application. Okay, namely in automotive, in aerospace, and in structural application. And for each application, you can name the type of composite that often used in those industry. Okay. All right. This is the following question. You may refer to the lecture slide given to you. Your lecturer already posted at the ULearn. You can download it. And also for self-enrichment, you can explore for answer through many sources available. Maybe you can go for the Googles and also textbook. All right. So let's have a look to the example related with the calculation, the pattern of calculation using having the calculation, the pattern of question that may be asked from this chapter. So for this part, the first part here, all right, cite the difference in large particle composite and dispersion strengthened composite. All right, for this question, you may refer to this slide related with the particulate reinforced composite. You can create the table of comparison here. The particle, the larger particle and dispersion strengthened particle reinforced composite. All right, so you can talk about the nature of the particle matrix interaction. So in the larger particle, the interaction is not go down to the just at the micrometer, but for the dispersion strength, the interaction is go down into molecular level. And then you can talk about the mechanical properties. The mechanical properties resulted due to having the large particle and dispersion strengthened. Also, you can name some of the few examples for each category. All right. So for the second question here, all right, read the question. A unidirectional Kevlar 49, we have the fiber reinforced composite polymers. Using the Kevlar 49 as our reinforcement phase. Okay, and we use epoxy as our matrix phase. Okay, so we extract all the information given here. Okay, they give the unidirectional Kevlar. So meaning to say something orientation like this, okay, contain about 60% by volume of Kevlar 49 fibers. So this is your VF equals with 60 volume percent. And then 40% of epoxy resin. So this is your VM, about 40 per volume percent. Okay, so the density for the Kevlar fibers, raw fibers equals with 1.45 gram per centimeter cube, and epoxy resin having the density as the raw matrix here equals with 1.2 gram per centimeter cube. Determine the weight percentage of Kevlar 49 and epoxy resin. Determine the weight percentage of Kevlar 49 and epoxy resin here in the composite. So calculate the density of the composite. Okay, so how to do this? Yeah. Okay, let's check if we have any empty space here. All right. So we already given all the information here, like VF 60 volume percent. We can write down as 0.60 weight, 0.60, and then VM here as 40 volume percent equals with 0.40 here. Rho F, the density of fibers equal 1.45 gram per centimeter cube. Rho M equals with 1.20 gram per centimeter cube. So the question asks you to find the weight percent of fiber, weight percent of matrix, and then the density of composite. Okay, so to do this, please have a look to our derivation in the lecture part 2. To calculate for the weight percent of fibers, we have this equation, rho F divided by rho F VF times rho M VM, okay, multiply with multiply with VF. Okay, just plug in all this value here. All right, we have the VF, VM, rho F, and rho M. All right, so just plug in the value 1.45 for the rho F, the density for fibers, divide by 0.6, the volume fraction of fibers, multiply with 1.45 plus with 0.40, the volume fraction of matrix, times 1.02 gram per centimeter square. Okay, terminate all this value, and then don't forget to multiply them with 0.60. Okay, so your answer will be 0.64 644 value, and then times with 100 to get in the form of percentage. Okay, what you can get is about 64.4 weight percent, okay, of fiber. All right, so to determine the weight percent of matrix, okay, so we understand that the weight fraction of fiber plus weight fraction of matrix equals with 1, the unity. So same goes to the weight percent of fiber plus weight percent of matrix equals with 100. So now we already determined the weight percent of fibers, and then to determine the weight percent of matrix, just minus 100 here with weight percent of fibers. 100 minus 64.4 weight percent. So you got the final answer about 35.6, sorry, weight percent of matrix. Okay, so to calculate for the density of composite, what you can do is, since the question giving is unidirectional, all right, meaning to say the longitudinal condition here. So based from the rule of mixture, we already have the equation like rho C equals with rho F, the density of fiber, times with the volume fraction of fibers, plus with the density of matrix, times with the volume fraction of matrix, equals with the overall density of composite. So just plug in the value given, the rho F, VF, rho M, and VM. 1.45 times 0.60, okay, plus with 1.20, times with 0.40. So what you can get is 1.35 gram per centimeter cube. So as you can see here, the density value of the composite basically are at between the density value of 1.2 gram per centimeter cube for raw matrix and 1.45 gram per centimeter cube for density of fibers. So we can simply say that our calculation is correct. Anyway, okay. So next, okay, wait, yes, right. So we proceed further to the example 3 here. All right, for the example 3, the question is local high-speed boat hull manufacturer. Okay, the boat body, the ship body based in Malacca, all right, produce their boat using a continuous and aligned. So if continuous and aligned, we can get back to the iso-strain case. Iso-strain case, using the rule of mixture, the iso-strain case always at the upper bound or upper limit performance. Okay, having the fiber reinforced composite consists of 40 volume percent of glass fiber. So the VF here equals with 0.40. Okay, and then having the modulus of elasticity 80 gigapascal. Okay, so the modulus of elasticity of fibers is 80 gigapascal and 60 volume percent of an epoxy resin. The VM here equals with 0.60, and then when the resin is hardened, it displays the modulus of about 4.7 gigapascal. So compute the modulus of elasticity of produced composite in the longitudinal direction. So if you deal with this question as simple as, okay, you extract all the data here, okay, you now to produce the body of the boat from the fiber. This is question 3A. Fiber, we align it, sorry, we continuous align the fiber, having the 40 volume percent with E fiber equals with Z 80 gigapascal, and then using the matrix epoxy having 60 volume percent, and the modulus of matrix when it hardened about 4.7 gigapascal. So find the E composite. So as simple as you use the upper limit equation, the isostrain condition, EMVM plus EFVF. Okay, just plug in the value, change it into 4.7 gigapascal times 0.60 plus 80 gigapascal for the modulus of elasticity for the fibers times with 0.40. Okay, the answer is about 34.82 gigapascal. So as you can see here, the answer for the modulus of elasticity of the composite just position at between the modulus of matrix. We have about 4.7 gigapascal, and then modulus of elasticity for fibers about 80 gigapascal. So the composite properties lay at the middle of this value between the modulus of elasticity of fibers and their other counterpart, the matrix counterpart. Okay, next. The question asks you compute the magnitude of load carried by the glass fiber reinforced composite, the magnitude carried, the FF, okay, if the cross-sectional area about 500 millimeter square. The A here is 550 millimeter square is taken, and the stress about 38 megapascal is applied in the longitudinal direction. Okay, what you can do here, okay, basically the answer is provided here, okay. We can just apply directly this equation, the relationship or the ratio between the fiber and also the loading to the matrix, okay. The relationship or the ratio, the force loaded to the fiber and also the matrix during the loading. We have FF over DFM, the ratio, EFVF over EMVM. Very simple to remember. The EFVF belongs to FF, the EMVM belongs to FM. Okay, so by changing all the by plugging all the data given, the EF given is 80 gigapascal, and then the VF about 0.4, the EM, okay, just now about 4.7 gigapascal, and then the VM about 0.6. Okay, we will have about FF over FM equals with 11.35, and then make it FF as our title of equation. So we will have 11.35 FM. So this is our first relationship. And then by having the data, the cross-sectional area and also the stress here, the AC given now about 550 mm squared, and then the sigma, the strength about 138 megapascal. Having the relationship of sigma equals with F over AC, the cross-sectional area of composite, we can calculate for the force loaded to the composite, the FC, by multiply the sigma, okay, with the cross-sectional area. So having 550 mm squared times 138 megapascal, or megapascal here we can change similar to Newton per millimeter squared. Okay, we can terminate for the millimeter squared here, all right, and then multiply between 550 to 138, we got about 75,900 Newton as our answer. So we understand that the FC equals with FF plus FM, because whatever force loaded to the fiber plus with whatever force loaded to the matrix will equals with the overall force loaded to the overall composite. Okay, so we already have this equation, FF equals with 11.35 FM. So just change this into this 11.35 FM plus FM equals with 75,900 Newton. So we got FM value. All right, after you got FM value, just change into this equation and calculate for the FF. At the end, you will have FF, the fiber load, the force loaded to the fiber, 69,754 Newton. So to answer this question, wait, yeah. Specialized processes have been developed for fiber reinforced polymer by using the open mold or closed mold. Pultrusion is one of the closed mold type method for PMC manufacturing to produce the product rod or beams. So please explain the pultrusion process. This is the schematic answer on how you can explain the pultrusion process. Remember that we need to have the fiber supply from the rack or krill holding roll, and then the fiber must be pulled and then must be wetted to the resin injection molding, resin impregnation tank here, so that the fiber can be wetted, all right, and then goes to the preforming die here so that we can compact the fiber into firm into the shape, and then go to the curing die, okay, for the consolidation and also for the curing process, and then we pull them, and then up to this stage, the fiber is already cured and then ready to cut into their specific product. Okay, so remember there are 5 stages here. The first stage, second stage, third, fourth, and the last, the puller parts. Okay, and as for summary, I think this is the end of the part 3 video of offline lecture for this composite chapter. So I wish you all can have in your mind now on how to classify the composite according to the matrix material used, and then also the reinforcement geometry. If the metric used, we can have the CMC, PMC, MMC based on their matrix type. And if we need to classify the composite based on the reinforcement geometry, we can have the particle type, the particle reinforced polymer PRF, particle reinforced polymer PRC. Okay, sorry. And then we have the fiber reinforced polymer FRP, and we have the sandwich structure based on the layers type, structure, laminate, or sandwich type. So producing the composite having their own objective, specific objective in its mind. Meaning to say, for different kind of composite, we have different purpose to develop the composite. Say, for example, for the MMC, we need to increase or enhance the properties like the sigma Y, the tensile, the yield strength, the tensile strength, and then the creep performance. But for the CMC, we are more interested to improve the toughness behavior due to the brittleness of the ceramic bodies. And then for the PMC, we need to increase all the related performance with the temperature performance. Okay, like to increase the creep performance, the modulus of elasticity, the yield strength, and the tensile strength at high temperature. So we have many kind of composite based on the geometrical classification, particularly reinforced, fiber reinforced, and structural. So I hope you can give a good revision to prepare for your final exam. So with that, I wish you all the best of luck and can score well in this interesting fundamental engineering subject, engineering material. So take care and have a nice day. Thank you, and I apology for any what we call that limitation during delivery of this video content. With that, I thank you. Assalamualaikum.